as you guys remember in last class, I kind of mentioned that decision trees was an important concept. It was a very important concept because element or fundamental model on which random forests, XGBoost, all these other advanced models are based on, right? So that kind of forms the fundamental piece to it. So can someone explain to me about the decision tree that you guys learned in last class? Can you tell me what's
A decision tree is splitting the data set into, in this case, into two something. There's a word for it. I don't remember. Based off of like the information we feed it. I guess the target we feed it. So it would decide if it's true and if it's false, and then it will keep splitting all the way until you get to the final where you can't split any further.
you guys kind of have it, but again, read up on decision trees, please, because the more you read up and the more you cement that concept, the better, because otherwise random forests and XGBoost is just gonna go over your head, right? So please read up about that, okay? Now, as you guys rightfully said, it is splitting the data set, and the way it splits the data set is by looking at each predictor, right? Why is it splitting the data set? Because it wants to cleave the data set into the classes, right? What we are trying to predict here is a specific variable, right, which tells us about the species of the iris flower. And this is the iris flower example, right? We had 4 features, which is petal width, petal length, sepal width, and sepal length, right? So what happens is, how does it cut the data set? You guys are right that it splits the data set, right? The entire data set. Starting over here in the first root node, right? I have my entire training data set here on top. What it looks at is, first it looks at one variable or one predictor, one feature, petal width. And it says that if for all the samples for where my petal width is less than or equal to 0.8, I'll go to the left. For all the samples where the petal width is greater than 0.8, I'll go to the right, right? That's how it is splitting. Let me start writing on the screen, just 1 second. Yeah, so that's how it's splitting the entire training data set, the whole training data set, into these 2 parts. Then it discovered that this part is already completely class 0, so it leaves it there. There is no further split, right? But here again, there are some mixture, right? It's not a clean split. There are class 1 and class 2 samples in this, right? Here what it does, again, it looks at the variable petal width. Is it less than or equal to 1.65 or greater than 1.65? Less than, it goes to this. Greater than, it goes to this, right? So like that, it keeps splitting the data set. You guys are right on that. But the way it splits it is by looking at the vector spaces, right, of each feature, and comes up with a pivot value. This is called a pivot value, right? Based on the pivot value of the feature, it splits the vector space into 2 groups or multiple groups, and then that's how it comes up with these samples, right? And yes, the last samples or the leaf nodes here that you have, they are the most refined subsets of data, right? Which clearly tell us, so there is no mixture here, right? So here, all the samples in this particular group are all class 1. All samples here are class 2. All samples here are class 2, all samples here are class 2, class 1, class 2, and class 1, right? And here class 0. Now, what did we discuss in last class? This is, what does this cause, right? If you allow it to split a lot, right? You remember we talked about the depth of the tree and the number of leaf nodes that I'm looking at and stuff like that, right? Controlling the leaf nodes, controlling the depth of the tree itself, right? Based on that, what am I trying to avoid?
Overfitting.
Correct. And overfitting basically means the model is a very complex model, right? It's a model with high variance. That is one of the drawbacks of decision trees, right? High variance. So, and that's the reason why we come up with these models like, where is this? Yep. These models called ensemble models. And one of the ensemble models is the random forest. Okay. So ensemble models, ensemble basically means that you bring together you use a couple of technique, right? Use a specific technique to bring together multiple models in order to put forth a more powerful model, right? Instead of coming up with one single model, right, which might be weak, which might be a decision forest with high variance, right? Very complex decision forest with high variance or low accuracy, right? Both of them are weak models, right? Instead, what you'll do is you'll come up with multiple trees, multiple weak models, you'll combine all of them and then come up with a stronger model, right? And that's exactly what ensemble models mean. They are combining techniques or combining multiple models in order to produce a more accurate model. Okay, now how does that happen? What exactly is, the idea of all of it is something that we are trying to look at, okay? So there are three different types of aggregation, right? When you are trying to like come up and combine these weaker models together, right? There are three different things. The things are listed here, right? Three different techniques are listed here. There is bagging, there is boosting, and there is stacking. Okay. In our course, we will not study stacking. We will study these two techniques, bagging and boosting. Okay. Now, so can you guys think of like, let's say you have like multiple decision trees, right? Instead of one decision tree, you have multiple decision trees. Can you guys tell me about two of the very common ways of like combining things? So let's say, for example, I'll give you an easy analogy to think about. Think of bulbs or electric connections, right? So there are two types of connections, or in electrical components as well, right? There are two types of, if you remember circuits, right? There are two types of connections.
You mean like positive and negative?
No, not that. If you're connecting electrical components.
So direct and alternating.
What did you say, David?
Really.
Direct and alternating current?
No, that is current. That's current, right? If you're connecting multiple components, electrical components in a circuit, right? Okay, for example,
closed circuit and open circuit.
Okay, let me draw that figure and then you guys guess. It looks like it's probably too generic of a field. Okay, let's say I have component 1 here, C1, C2, C3. Okay, this is one circuit. Then this is C1, C2, C3. Can you guys tell me these two? These are the two types I'm referring to.
What is that?
The bottom one is sequential, maybe?
Yep, bottom one is sequential or series connections, right?
Yeah.
This is parallel, right? This is parallel connections, right?
Yeah.
One
How?
This is parallel connection, right? Because you have C1, C2, C3.
The load is split between the three branches.
Yep.
But in the second one, it goes from one to the next to the next.
Exactly.
David, I see what you mean now.
Yep.
So one is stacked and one is like just flows.
Exactly, right? So one is where, so even in processing, right? This is true in processing as well. There is sequential processing, there is parallel processing, right? So, that's exactly what's happening here in these two techniques. Bagging is a technique of parallel processing. Boosting is a technique of sequential processing. That's exactly what both of them are. So stacking is a whole different thing. It's kind of like, think of stacking as like combination of bagging and boosting. So you have parallel models which are stacked on top of each other or sequentially learning from each other. So I'll explain bagging and boosting in our class. So we are going to learn about advanced techniques like random forest and XGBoost. Now, random forest is based on the bagging technique. XGBoost is based on the boosting technique. You see that from the figure here as well, right? So bagging is the technique behind random forest. Boosting is the technique behind gradient boosting, which includes XGBoost. Okay. So now let's move forward and discuss about bagging as a technique itself, right? So what happens in bagging is that you have, so in a decision tree, right? In a typical, let's take the iris data set example itself, because also in the notes, right? The class notebook, that's the same data set taken as an example. Okay. So let's say you guys refer to this particular diagram that we have here, right? So let's kind of recreate this here. So I have the first root node where I'm looking at petal width. 0.8 is my pivot value. I have two nodes. I have something else here, and then I'm looking at petal width, another value of petal width. Then I'm looking at, say, sepal length. Then I'm looking at sepal width here or something like that. Okay, this is how my tree looks like, right? If I just construct a simple decision tree, this is how it would look like, right? But in this technique, right, like in ensemble methods, what we do is a single tree might be prone to high variance, right? Which means that it will learn from the noise in my data and try to overfit to the data, right? If I don't control it, what happens? If I control it, it might give me very low accuracy, right? Or if I don't control it, it will give me higher accuracy, but I might be overfitting. So that's the issue. It might not actually hit the sweet spot of the right accuracy and not overfitting stuff, right? I might or might not get that with a single decision tree, right? So what I do is, this is my single decision tree, which is splitting my data in this fashion, right? Now, have you guys thought in last class when we discussed that, hey, my pivot value is 0.8 for petal width, right? Have you guys thought about like how this value we come up with, and like why that value can we not have another value?
No.
Why didn't you guys think about it?
I thought it was just a random value that would just.
Okay, yes, that's good. So if it's a random value, why can't I have another random value?
You can, I guess.
Right? Exactly. So, and that's the whole idea of ensemble methods, right? Because the idea here is that if this is a single tree, it is going to split my training data set in this fashion. So it will say, okay, petal width, then I'm looking at petal width again, sepal length and sepal width, and then I look at petal length somewhere down, right? But is it the right way or the right split? I don't know. So this is doing things a certain way. Why not take another tree, right, which is doing things in a different way, right, which looks at a different training set? So here also my training data set, right, my training data set, it has row 1, 2, 3, so on up to row, say, 100. Okay, let's say I have 100 rows. So it will look through this training data set in this particular order, right? Now, what if I shuffle my data, right? And based on this order that it sees, it is probably taking petal width as the first splitter. What if I reorder my data and have like 51, 63, 42, so on, up to 100? But again, all these values are shifted, right? Shuffled around. Now it's almost like a different training set. And then it might come up with a different set of, it might say sepal width. My first separation variable is sepal width. I get these two data. Then I look at sepal length. Then I'll get something else, right? You guys get that, right? So a different tree could definitely be constructed, and a shuffled training data set might be shown to the model, right? Have you guys come across this kind of shuffling anywhere else previously? Guys, can you think of a situation where you came up with this kind of a shuffling? DS2,
Mm,
K-fold cross-validation,
yes, that one.
right? Do the others remember?
A little bit. I remember the term, but I don't remember
Yeah.
what it did.
So K-fold cross-validation, what happened? You have like training and test split in a typical CV, right? In K-fold cross-validation, you do the same CV K number of times, but what happens is each time you pick a different test set, right? So you're picking a different training set as well. First time you might be picking rows 1 to 80 out of the 100. Second time you will pick something from 33 all the way to say 93 or something, right? So something like that. So you're going to pick different rows to train each time. Thereby, and then at the end, you will average out your accuracies, right? Because doing CV once versus doing CV multiple times, it's always better to do it multiple times so that you are training the model on different training data sets. You're exposing it to different training data sets, and it doesn't have any, what do you call? It is exposed to the entirety of the data set, and at the same time, it's not learning from noise with a specific training set. You're exposing it to all the, what do you call, rows of data, all the samples in your data set, right? And you're averaging things out. So even if you get in one specific iteration of training, your accuracy probably might be like 95% or something. The other sets might be performing poorly, but when you average it out, you will get a aggregate accuracy metric, which is much more reliable than a single CV, right? The same way, it's kind of similar concept, right? Here. So instead of relying on a single tree, which might be prone, single decision tree, which might be prone to high variance because it tries to overfit to the training data, you take multiple trees, train them with shuffled training data sets, right? And then the split might be totally different, right? This is the concept of bagging. What you do at the end is you'll have like multiple trees. Let's say I trained for number of trees is, let's say 5. So I have 5 different decision trees, right? Now I will be taking the outputs of all these 5 trees, right? And then deciding upon what my prediction is going to look like. That is bagging. And it's almost like a simultaneous or like a parallel processing, because you're training 5 different trees in isolation and you're combining their outputs at the end. Do you guys understand so far?
Trying.
Yeah, I think I do.
Yep. It's almost like training decision trees 5 times, but on a shuffled training data set. Instead of having rows 1 to 100 in the same sequence, you shuffle them around so that you get different trees, right? Now, and this is the concept of bagging, okay? Random forest is an extension of bagging. So apart from the new tree, right? Apart from just selecting or like shuffling from this training data set, it also shortens the predictors that the tree is looking at, which means, let me rub this off. Any guesses what that means? If it's going to select from the predictors?
Is it underfitting?
It might underfit as a single tree, but we are anyways combining them, right? But what's going to happen is, so in my iris data set, I have 4 predictors, correct? Sepal length, sepal width, petal length, and petal width, correct? So when I train a decision tree, right? When I train a single decision tree, right? It looks at how many features is it looking to split come up with the split of the sample data set?
30%.
Wait,
No. Yes, the training data set is like 70%, correct. And that's what it is working with. But how many features of the data set is it looking at to make these
Oh.
splits?
all 4.
Yes, that's correct, Susan. So all 4, right? Now, in bagging as well, what happened with bagging? We are training multiple trees, tree 1, tree 2, so on, right? Tree 3, so on. They are all looking at 4 predictors, right? The difference between these 3 trees is the training data set. So instead of having rows 1 to 100 in this order, it will have the rows 1 to 100 in a different order. This will have it in a different order. Thereby, the trees will differ. Now, with random forest, what happens is, I want to further make sure that none of these trees are correlated. Okay. So when I want to avoid, and why we want to avoid correlation is beautifully given in an article that I will share with you guys. Okay. So in T1, I won't expose all the 4 features. Instead, I will say you have only 3 features to pick from. So I will construct the first tree with only sepal length, sepal width, and petal width. I will leave out petal length. The second tree, I will again construct with only 3, predictors. So I will do sepal width, petal length, and petal width. So apart from making the tree look at shuffled training data, we will also limit the feature space. That way, I get a totally different tree here. I get a totally different tree here. I get a totally different tree here. There is no chance of any parts of the tree also matching. Okay. So by the way, and that's exactly how a random forest model differs from bagging, right? It's the same as bagging. It's a slight extension that it doesn't just filter from the training data set or shuffle the training data set. It also filters the feature set. So instead of exposing the tree or building the tree from all 4 features, you build the tree only from 3 features at a time or something like that, so that you get a different tree each time. And you're not like correlating, you're not getting highly correlated models. You're getting very different models and you're learning from the differences. Okay. Now, how do they combine the results at the end of these training, right? Because this is a different model. This is a different model. We have 3 different models in bagging or 3 different models in random forest. So how are we combining the results, right? So here what happens is, if it's a regression, right? It's a simple aggregation. So what we do is, if it's a regression, model 1 will predict a specific value for my target, right? So I will supply it with some test predictor values, right? And what I get is a Y predicted Y value, right? What happens here is, I will get a Y predicted value here, Y1 pred. I will get Y2 pred here. I will get Y3 pred here. For regression, I can simply average out these 3 Y predicted values and say that that is my final prediction.
Yeah, so you
Because-
average the 3 and make that one Y predictor.
Correct, right? So 1 predicted Y value, right? Whatever the target value it is, I will average it out. In the same way for accuracy as well, right? If someone asks me what's the accuracy of my bagging decision trees model, I will bagging classifier or bagging regressor, so to say, right? For bagging regressor, what I will say is, I will calculate the accuracy of model 1, model 2, model 3, and average out the accuracies. And that's what my average accuracy is of the entire bagging regressor model will be. For predictions, the same thing. I get prediction 1, prediction 2, prediction 3, I will average out. Right? That is simple, straightforward for the regression. Now, what if I am training a classification model? In case of a classification model, I will get a class variable here, right? I will say class 0. Model 1 says class 0 of iris data set, right? Model 2 says, what does it say? Class, give me a number between 0 and 2.
1,
Okay, 1. What does model 3 say? Class
2.
let's pick one of 0 or 1. Let's not make our lives difficult.
One.
Pick one of 0
Zero.
or 1.
0, okay. Let's pick 0, right? So let's say if these are the predictions that I got from all the 3 models in my bagging classifier model, right? So I have 3 decision tree classifiers, each working on a different shuffle training data set. And first one says it's class 0, second one says class 1, third one says class 0. I will see maximum number of votes, right, for class. And I will say that 2 votes for 0, and my final prediction is going to be 0.
What
Yeah.
if we get different numbers?
What if we get 0, 0, 0, 0? Oh no, then it will be 0.
Yeah,
Correct.
but what if we get 0, 1, 2?
Correct.
You can't
So
be
if-
0, 1, 2.
Yeah,
Is
let's
it-
assume that is 0, 1, 2, right? And unfortunately, if you have only 3, so to say, models, right? What's going to happen is it's probably going to throw one of these numbers randomly, or you can select them based on whichever model you feel has a higher classification rate, classification accuracy, right? The accuracy score is based on how many misclassifications it does for each thing, right? That's something that you can do. But the better thing to do still is increase your number of estimators. If you have 3 classifiers, don't train 3 trees. You can run into this problem, right? If you have 3 classes, train more number of trees, at least greater than 3 trees. Make sense?
Yeah.
Because that way you will have definitely at least 1 repetition.
So if we have 3 classes, we should train more than 3
Yep.
models.
Correct. You should train for more than 3 estimators. So train 3 models in the sense, I'll show you the code, right? You guys don't have to train each of these decision trees, right? Let me go back to the notebook. Where is it? Here it is, right? So for bagging classifier, the code is just this. Okay. This is a bagging classifier. This is, this is a bagging regressor. This is a bagging classifier. Okay. So let me show you guys quickly. Bagging classifier. Okay. So sklearn.ensemble bagging classifier. Okay. Now here, n estimators is a parameter that you commonly see in these ensemble methods. This basically tells me how many number of weaker models I'm going to train, right? So here, if I mention, I'll just mention n estimators here. Let me see. Yeah, here, right? N estimators. I gave 100 here. So think of this as 100 different decision trees that this model is training by default. You don't have to create decision tree. You don't have to create 100 models. Okay. By default, it's going to use the decision tree and it's going to build these decision trees based on shuffle training data. It's going to take care of everything. Only thing you need to do is apply this model as you would apply every other model. The thing that you need to identify here is n estimators is 100. Max features 3, which means I'm trying to control the feature space as well. Okay. If I don't give this, it will expose each decision tree, like how we discussed, right? Each decision tree will be exposed to all the features. If I am controlling this parameter, then I'm kind of like making it similar to the random forest as well. Again, max features. Random forest also has a similar parameters, right? And here it says the results from both models are same, as random forest is just an extension of the bagging technique. Okay. And in this case, that extension is looking at the max features, but there is a feature to control that here as well. You can control the feature space here as well. Since we did the same, since we controlled it in bagging regressor or bagging classifier as well, it became equivalent to a random forest.